Okay, so today I'll be going through an overview of electrochemistry part 2 with the focus being on electrolytic cell. So recall last video in a galvanic cell, the reaction is a spontaneous redox reaction where electrons spontaneously flow from the anode to the cathode, right? And we make these electrons flow through an external circuit so as to power an electric load, for example, a light bulb, right? And all batteries, right, regardless of whether it is the lithium-ion battery in your phone or the non-rechargeable zinc battery, the old kinds of mercury-containing batteries, or the car battery, right, in your car, right, they are all galvanic cells, and it's named after Galvani, who is the inventor of the first battery. In contrast, though, in an electrolytic cell, electric current is passed through an electrolyte to force an otherwise unspontaneous redox reaction to occur. So while in a galvanic cell, there is a spontaneous reaction being occurring and you're harvesting this spontaneous chemical reaction to produce a current. In an electrolytic cell, sort of the reverse occurs. We are putting in an electric current to force an unspontaneous redox reaction to occur. So immediately we can see that we can create a very simple circuit, right, by connecting an electrolytic cell to a galvanic cell. So the galvanic cell generates the current which goes into the electrolytic cell to generate the unspontaneous chemical reaction. That is the question we normally see in exams. And so usually we do not see, for example, sodium chloride solution spontaneously giving off hydrogen and oxygen gas. However, when the dilute sodium chloride solution is electrolyzed, one end of the electrolyte has electrons pumped in, right, by connection to the negative end of a battery. This is the cathode where reduction occurs, while the other end of the electrolyte has electrons forcefully drawn out by connection to the positive end of the battery, and this is the anode where oxidation occurs, right, since oxidation is loss of electrons. So let us take a look at the cathode where electrons are pumped in, right? There are a few species which can accept these electrons, or in other words, since reduction is gain of electrons, we can say that there are a few species which can be reduced, right? Na plus present from the sodium chloride, H plus, right, and H2O. However, so from this, right, you appear that H plus is most likely reduced, right? Why? Because we learned that for a reduction process, the more positive the electrode potential is for the reduction process, the more favorable the reduction process is. However, recall, where is the H plus coming from? Alright, in the neutral solution, it comes from the self-ionization, the auto-ionization of water. However, its concentration is very, very low. It's only 10 to the power minus 7 mole per dm cube for a neutral solution, much lower than standard conditions of 1 mole per dm cube, at which E naught is measured. Hence, the real value of E for that reduction is likely much more negative and much less favorable. Hence, it is actually water which is reduced and H2 gas effervesces out. At the anode, where electrons are drawn out, there are a few species which can give off these electrons. In other words, I can say that there are a few species being oxidized, since oxidation is loss of electrons. So I'll write the equations below in terms of the reduction potentials. Why? Because that's what E naught values in our data booklet refers to. But in this case, the species being oxidized, I write it on the right hand side. So there are a few species, for example, the chloride anion from the sodium chloride, they are dissolved to form the NaCl solution, hydroxide anions, and the water molecules. So recall that the less positive the E naught value, the more likely it is that oxidation, which is the reverse reaction of the reduction process, will occur. Hence, it will appear that OH minus will be the one being oxidized. But notice that concentration of OH minus is also very low, right? 10 to the power minus 7 mole per dm cube for a pH neutral solution, right? Much less than 1.0 mole per dm cube, which is the concentration at which this E naught of plus 0.40 volts is measured. Hence, the real E for the oxidation of OH minus is likely to be very much more positive, and thus the real E for the reduction of O2 to OH minus is likely to be very much more positive, and thus the oxidation of OH minus is very likely to be much more unfavorable. Hence, water is the species oxidized and oxygen gas effervesces out. And the overall reaction, we just add the cathodic and the anodic half equations together, we get the decomposition of water into hydrogen and oxygen gas, with the E cell being the cathode minus the anode, right, getting minus 2.06 volts. And notice it's negative, so this indicates that the reaction does not occur on its own spontaneously. Hence, a potential difference of at least 2.06 volts in the opposite direction is needed to drive the electrolysis of sodium chloride solution. So if you are given certain information, can we calculate to what extent the electrolysis occurs? Yes, we can, but I need to go back to the fundamental physics definitions. So by definition, the current is defined as the rate of flow of electric charge with respect to time. And so you can write that I equals to dq dt. And for constant current I also equals to delta Q over delta T. Hence, for the application of a constant current I for a duration T, the charge transferred Q equals to IT, where Q is in coulombs, I is in amperes, and T is in seconds. But what constitutes this charge, right? Electrons. Fundamentally, they are electrons. We want to know the amount of electron transferred, and we want to know it in moles. Why in moles? Because chemists like to handle large quantities in terms of the number of moles to make the values much more easy to handle. Hence, we need Faraday's constant, which tells us the charge of 1 mole of electrons. Right, and so we can easily say that the number of moles of electrons is equal to the total charge divided by the charge per mole of electrons, right, F, where F is Faraday's constant, 96,500 coulombs per mole, and is found in your data booklet. So let's look at an example question. Okay. So when 1 mole per dm cube of copper sulfate solution is electrolyzed by copper electrodes under a current of 1 ampere for 10 minutes, right, what is the increase in mass of the cathode? So we can find the number of electrons. Let's first find the total charge that has been transferred, right? So it's 1 ampere times 10 minutes, but remember the time must be in seconds. So equals to 600 coulombs. And then we can find the number of electrons equals to the total charge divided by charge per mole of electrons. And hold on, let me see what that will be. Yes, that will be a value of 0.0062176 moles. So note that for the formation of every mole of copper, right, from a copper 2 solution, we need 2 moles of electrons. So by simple stoichiometry, the number of moles of copper is half that of the number of moles of electrons being transferred, right? So this is the number of moles of copper formed. So can we find what's the increase in mass of the cathode? It's the mass of copper formed, am I right? So it's just the number of moles of copper multiplied by the molar mass of copper, which is 63.5. And what do you get? You get 0.197 grams. Okay, so get it? This is a very easy example. You will encounter slightly more challenging examples in say your school's exam papers or practice or worksheets, and be prepared lah, but it will not be too difficult. So there are certain 2 examples of electrolysis that you need to know. The first is anodization of aluminium, which is basically forming a coating of aluminium trioxide on the surface of aluminium. Why do we want to do that? Because this oxide layer protects the underlying aluminium from being oxidized. And in addition, we can put all sorts of interesting colored dyes which can bind chemically to the aluminium oxide layer, and thus providing aluminium with a wide range of interesting and delightful colors. So at the cathode, the following species can be reduced. So what we are doing is we're electrolyzing a solution H2SO4 with aluminium as the anode and an inert graphite electrode as the cathode. So let us first look at what happens at the cathode. So the following species can be reduced: H+, SO4 2-, and H2O. So it may appear that SO4 2- will be preferentially reduced, right? Because it has a most positive inert value. But recall that concentration of H+ is twice that of SO4 2-, right? And hence the real E value of the reduction of H+ is likely to be much more positive. And H2 gas is actually the one being effervescence out. At the anode, the following species can be oxidized, right? Once again, I rewrite it as reduction potentials, but with the species that are being oxidized on the right hand side. From the inert values, H2O will be more preferentially oxidized, right? Because it has a less positive reduction potential, and thus O2 gas will be produced at the aluminium anode. The liberated O2 gas then reacts with the aluminium cathode to form Al2O3, right? And so note that aluminium is eventually oxidized, but it's not directly oxidized by the application of the electric current, but instead is being oxidized by oxygen, which is a product of the electrolysis of the H2SO4 solution. So let us take a look at the next example, the purification of copper. So on one end, right, the anode is the impure copper, and the cathode is a sample of pure copper, an ingot of pure copper. And what is the electrolyte? The electrolyte is copper 2 sulfate solution. So at the impure copper anode, right, impurities more reactive than copper will first be preferentially oxidized, right, because it has a less positive, or in this case more negative, reduction potential. Once that's done, copper will then be oxidized, right? After all the impurities more reactive than copper, what will be oxidized, right? It will be copper. So impurities less reactive than copper will be oxidized after all the copper has been oxidized, right? Theoretically, yes, but actually no. Why? Because these impurities, right, will no longer be physically connected to the external circuit once the entire copper anode has dissolved, right, has been oxidized into a solution. So what happens to these impurities? They just drift down and fall to the base of the solution as anodic sludge, right? And the nice shiny metals like silver, gold, platinum, all these less reactive than copper can be then extracted by further processes. So at the pure copper case, the impurities more reactive than copper will not be preferentially reduced. Why? Because the reduction potentials are less positive than our copper and too negative, right? For zinc, for example, to be reduced. Instead, copper is preferentially reduced. Hence, more pure copper is added to the pure copper electrode, and the pure copper ingot increases in mass. So effectively, what is happening is that the copper is transferred from the impure copper anode to the pure copper cathode. So what this is observed is a purification, right, of copper. Why? Because the pure copper ingot gains more pure copper, right, and while the impure copper dissolves. Okay, so that's the end of today's crash course, and I hope that it has been useful to you.